In this video, we are going to discuss the span of a subspace and the null and range of a matrix. We will start by reviewing linear combinations and linear dependence. We'll move on to span. We'll define what a span is and do some examples. And then we'll go and finish with null space and range of a matrix. We will start by reviewing Y is a linear combination of n vectors v1, v2 up to vn. If there exist scalars, one scalar for each of the vectors a1, a2 up to an, such that y equals, and this is what the linear combination is, a scalar times v1 plus a different scalar times v2, or possibly a different scalar plus v2, up to a scalar times vn. The other review we need is linear dependence and independence. So vectors are considered linearly dependent if there is a non-trivial solution to the linear equation where a1 v1 plus a2 v2 plus up to ap vp is equal to 0. So there's a non-trivial solution to the linear combination equals 0. It's linearly independent if there's only the trivial solution to this homogeneous equation. And now we have a theorem that will help us define span. And this theorem I try to summarize it in parentheses, name the theorem, but it almost is a restatement of the theorem. But anyway, so the name is the set of all linear combinations of a vector, of a set of vectors, is a subspace of Rn. So if S is equal to the vectors v1, v2 up to vn, and these are vectors in Rn, then the set W consisting of all linear combinations of these vectors is a subset of Rn, and we denote it with span of S. For this proof, in order to prove that W is a subspace of Rn, we have this theorem that says to prove something is a subspace of a vector space, we just need to show the zero vector is in W, that addition is closed in W, and scalar multiplication is closed in W. So first, the zero vector is in a1 v1 plus a2 v2 plus up to an vn. And essentially, if you set each of these an's, or each of these scalars, equal to 0, then you see that you can have a linear combination whose sum is equal to 0. You can see if you have a linear combination equal to A, so A is equal to A1 V1, A2 V2 up to A and Vn, and then B is a second linear combination with B1 V1, B2 V2 up to Bn Vn, and the idea is these A1s, A2s, and Ans, and B1s, B2s, and Bns, these are all scalar multiples multiplying by the vectors V. Then A plus B is equal to A1 plus B1, the two scalars, times V1, A2 plus V2 times the scalars, times the vector V2, up to An plus Bn times the vector Vn, which is another linear combination of the vectors V1 through Vn. So this sum of A plus B is still in W, so it is closed. And last, if we multiply a scalar times a linear combination of our vectors, we're going to get alpha times, here's our linear combination, we just get back another linear combination. So scalar multiplication is closed, and W is a subspace. The subspace W, consisting of all linear combinations of a set of vectors v1 to vn, is called the subspace spanned by S, and is denoted with SPS or SP, and then you list out the vectors. Our first example is the span of a single vector, and we see that it is aligned here. So for example, if our vector is equal to 2, 1, we want all linear combinations of our vectors. Well, there's only one vector, v is equal to 2, 1, and all linear combinations means we're going to multiply it by all possible scalars, a1. So if we multiply this vector by 2, we get this point. If we multiply by 1 and 1/2, we get something like this. Multiply by half, we get this point. Multiply by negative, and we get this point. But you can see that all of these points we get as we scale v, we have this point on the line. Our second example is the span of two linearly independent vectors is a plane. So here's an example, U and V. These are linearly independent, and the importance here for the two vectors is they are not collinear. So it's not it's not like U plus this blue vector here, which is really very much the same vector as u, except shorter. I had talked about the span of a single line, so if we consider multiplying u times all the different scalars we can have, we're just going to extend this line here, and when we multiply by negative in scalars, we're going to extend u this direction, whereas v, as we multiply by scalars, positive scalars, we extend v out this way, and by negative v, we extend v out in the opposite direction. I have covered this example in a little more detail in an earlier video. It's sort of supplemental about kind of some examples on giving intuition behind vector spaces. So I'm going to cover this very briefly in this video. So I've extended v, I've extended u, and the idea is now when we add different scalings of u to different scalings of v, we'll get the whole plane, the entire plane. So for example, just starting with u plus v, and we just use our parallelogram law, we will get this point here. When we scale u with something a little bit shorter than u, and scale v with something so that we have a vector a little bit shorter than v, then we get a point inside this parallelogram that's defined by the two vectors u and v. When we scale u over here by something a little longer than u, and scale v by something a little longer than v, then we're going to start to extend basically our parallelogram, and then we'll get something out here. Next, we'll take something a little shorter than u, but something longer than v, and we get this point over here. So essentially, what we're doing is by taking positive scalings of u and v is we get all of this kind of quadrant of this plane. When we do something similar, adding negative v to negative u, we're going to get this quadrant of the plane. When we take negative v with positive u, we'll get this quadrant, and finally, negative u and positive v will get this quadrant. So all possible scalings of u added with all possible scalings of v is going to give us the entire plane, or an entire plane. So why do we need the vectors to be linearly independent? Well, collinear vectors do not span a plane. They just span a line, because if this is collinear, if u and this blue vector are collinear, we're not going to span a plane with that. We're just going to span a line. So if two vectors are linearly dependent, so a1v1 plus a2v2, what that tells us is we can solve for v1, and we see that it's just a rescaling of v2. So in other words, linearly dependent, two linearly dependent vectors are always collinear. So next we have this larger example. Let's say u is equal to 2, 1, 0, and v is equal to 0, 1, 2. We want to determine the span of u and v and give a geometric interpretation of this span. By definition, my span is equal to all the linear combinations of u plus v. So if I name my scalar multiples x1 and x2, it's x1u plus x2v, or written in vector form, looks like x1 times my vector plus x2 times my vector v. So in other words, w here, this vector w, is in the span if this part of the equation, this matrix A, which comes from these two vectors, u and v, times the vector x, you can verify this gives you the same as this linear combination here. If you can find x1 and x2, that solves this matrix equation. And we can solve this matrix equation by using this augmented matrix of A times our vector w, which is row equivalent to this matrix 2, 0, w1, 0, 2, w2, 0, 0, minus 1 half w1 plus w2 minus 1 half w3, which implies that w1 equal minus 2w2 plus w3 equals 0. And last then, our vectors w look like x, y, z, such that x minus 2y plus z equals 0. So I could have left this as w1 minus 2w2 minus w3 equals 0. But I wrote it this way because this is easier to see that this is an equation of a plane. So that's our geometric interpretation. This next example is to let V be the vector space of real 2 by 2 matrices, and W is the subspace defined here, which is the matrices with zeros on the diagonal and real numbers for the other entries. Find a spanning set for W. By definition, a spanning set, and I happen to know there's two, but it could go from V1 to Vn, right? A number of vectors such that when you multiply by scalars, you get this matrix. And it just so happens that our vectors here are actually 2 by 2 matrices, right? Because V is a vector space of 2 by 2 matrices. So I want to multiply a scalar times A1, my first matrix, plus another scalar times A2, and get this matrix here. And just a word on why I said I thought there would be two vectors or two matrices that would span the space. It's because I'm looking at these variables here, A12 and A21, and there's only two variables, so I should be able to cover it with two vectors. This will become more clear once you see the solution. So I rewrote what we just said in a different notation. So I want the span in my two vectors, which happen to be 2 by 2 matrices, A1 and A2, to be equal to any matrix with zeros on the diagonal, and the entry A12 possibly non-zero, and the entry A21 possibly non-zero. And then I wrote that one more time. This needs to be a linear combination. So I use the definition of span to write this as a linear combination, alpha 1, A1, matrix A1, plus alpha 2, A2. So this is what I'm looking for, an A1, A2 that I can express a general 2 by 2 matrix with zeros on the diagonal. I can do that if I set A1 to the matrix with 0 everywhere except for the A12 entry, and A2 0 everywhere except for the A21 entry. So you can see this general matrix can be equal to A12 times my matrix A1 plus A21 times my matrix A2, and therefore these two matrices here, A1 and A2, span the space of W. My next example is let W be the subspace of P2, and remember P2 is the space of polynomials of degree 2 or less. This is the general form of P2. And we're going to let W be the subspace such that the polynomial is such that A2, this last coefficient, is equal to minus A1 plus 2A naught. We want to exhibit a spanning space for W. And just to remind you what this space looks like, the vectors are just polynomials of degree 2 or less, so one vector would look like 1 plus x squared. Another vector might be 1 plus 2x squared, just anything of this form. The 0 vector is equal to 0, so P2 inverse would be minus 1 minus 2x squared, because when you add these two, this is the additive inverse, when you add these two, you get equal to 1. Also, the multiplicative identity, I already have this, so I'm just going to call this P3, would just be equal to 1, because this polynomial times any of these other polynomials just gives you back the original polynomial. We had proven in a previous video that this space, P2, is a vector space. Now we want to look at vectors, and I'm going to take a guess that it's 2, P1 and P2, such that the span is equal to A naught, A1x, and then I plugged in this A2 over here into times x squared, because we're given that A2 is equal to minus A1 plus 2A naught. Now just a word on how I guessed that there were two vectors that would span the space. I can look here at my constants, my scalars, A naught, A1, and A2, and I see that here the A2 becomes dependent on A1 and A2, so I really only have two variables, A1 and A naught, to worry about. To sort of isolate what this A naught and this A1 variable are doing, I set A naught equal to 1 and A1 equal to 0, and then on the next step, I set A0 equal to 0 and A1 equal to 1, again because I want to isolate what's going on with the A naught and A1. So when I set A naught equal to 1, what I get is P1, my first vector. So you can see I plugged in 1 for A naught and 0 for A1. and I get 1 minus x squared. Similarly, when I look at when I try to isolate what's happening with a1, I set a1 equals to 1 over here, and a naught equals to 0, and I get x plus x squared. And now when I take a linear combination of my p1 and p2, so I have a naught times p1 plus a1 times p2, you can see that's equal to a naught plus 2a naught x2 plus a1x minus a1x squared, which means my term for for x naught is equal to a naught, which is what I wanted. My term for the x is just a1, which is what I wanted. And my term for the x squared is 2a naught minus a1, which is exactly what I wanted for w. So therefore, my 1 minus x squared and my x minus x squared vectors span the space of w. Now that we've talked about span, we are ready to talk about null space and range of a matrix. So the null space of a matrix, of an M by N matrix, also called the kernel, is denoted the script n of A or null of A, and it's the subset of vectors in Rn defined by x, such that Ax equals 0 for x in Rn. So in other words, it's the vectors x that A maps to 0. And there's a theorem that says the null space is a subspace of Rn. And we will do that proof. And to prove something is a subspace, we have 3 things to show: that the 0 vector is in W, the addition is closed, and scalar multiplication is closed. So first, we can look at x. X equals the 0 vector. When we multiply a times x, or a times the 0 vector, we're going to get 0. Therefore, the null space contains the additive identity. Now, for S2, addition is closed. We're going to take 2 vectors u and v such that a times u equals 0 and a times v is equal to 0. And we need to show when we add u plus v together, that a times u plus v is still equal to 0. To show this, I'm going to use this theorem of distributive properties of matrices, where a plus b times c is equal to ac plus bc. And so here I'm considering u and v, even though they're vectors, they're basically matrices with one column. So u and v are n by 1 matrices, so then a times u plus v is equal to au plus av, which is just equal to 0 plus 0, which is equal to the 0 vector. Therefore, addition is closed. For S3, to show scalar multiplication is closed, we need to show that if a times the vector u equals 0, then a times alpha u is equal to 0. But here I'm using just properties of matrix multiplication. I can pull out the alpha. Again, this is from matrix multiplication. And then I have alpha times au, which is just 0. So I get the 0 vector. And therefore, this null space satisfies S1, S2, and 3, and therefore is a subspace of Rn. And now we will do an example where we will describe the null space of a matrix A, where A is the matrix 1, 1, 3, 1, 2, 1, 5, 4, 1, 2, 4, negative 1. By definition of the null space, that's just simply the x, the vectors x, such that ax is equal to 0. So I've written ax is equal to my 0 vector. But we know how to solve this. We use the augmented matrix of A plus our 0 vector, which is row equivalent to this matrix here: 1, 1, 3, 1, 0, 0, negative 1, negative 1, 2, 0, 0, 0, 0, 0, 0. Sometimes I write these little, the x vector down here so I can remember this column is multiplied by x1, this column is multiplied by x2, and this is x3, and this is x4. So then I can write this here. So what I have is I have 0 on the bottom, so I'm going to have free variables, and I notice this tells me that x2 is dependent on x3 and x4. And I wrote out how it was dependent here, which means also x3 and x4 are free. And now when I look at this top line, this tells me x1 plus x2 plus 3x3 plus x4 equals 0. Or in other words, x1 is equal to minus 2x3 minus 3x4. So putting this all together, what I have is that the vector x looks like x1, which is minus 2x3 minus 3x4, x2, which is minus x3 plus 2x4, x3 and x4. So what that tells me is any vector x can be written as minus 2, minus 1, 1, and there's no x3 term here, so that's 0 times x3, plus, and now I'm looking at my x4 terms, I have minus 3 plus 2, there's no x4 term here, so that's 0, and then 1 x4, which means all vectors x are a linear combination of minus 2, minus 1, 1, 0, and minus 3, 2, 0, 1. I've written that out here, so x is a linear combination of these two vectors, and if you recall, two vectors will span a plane. For our next example, we are going to verify any plane through the origin and R3 is a subspace of R3. And just a reminder, the equation of a plane in R3 through the origin is given by ax plus by plus cz, where a, b, and c are scalars specified, and they're not all equal to 0. Using this equation, we see that a plane can be represented by ax equals 0, where a is equal to a, b, and c. So we have a, b, c multiplied by x, y, and z. So you can multiply this out and see that you get the equation of the plane. Thus, x is on the plane if x is in the null space of A. And since the null space of A is a subspace of R3, any plane through the origin is a subspace. Okay, now that we've gone through null space, we're ready to go on to range. Range is sort of analogous to functions where you take a set A and whatever set these elements map to was considered your range, right? And A was considered your domain. So this idea of range is totally analogous here. In particular, for a matrix A, which is M by N, the range of A denoted range of A, sometimes it's denoted with a script R, is a set of vectors in Rn defined by range of A is equal to the vectors y, such that y is equal to ax. So again, it's whatever gets mapped to by A. So this fact here is really helpful for finding the range of A. The range of A is all vectors y, such that the linear system ax equals y is consistent. And another fact that's helpful is axy is equivalent to, if you recall, that we can then multiply each component of x by its corresponding column vector of A. So range of A, looking at this form, is equal to the span of the column vectors of A. So this is also very helpful for finding range of A. And I'm just going to look at how we rewrote this matrix equation ax equals y as a linear combination of the column vectors. This is a really important thing for you to be able to do. We had mentioned it before, way back in chapter 1, but I want to go through it one more time to make sure you're totally comfortable with it, and it's something you really do want to be able to pull out very, very quickly and easily. It should become natural to you. So my matrix equation ax equals y looks like this. Here I rewrote A as to be a 3 by 3 matrix for this example. And then I have x, then my column vector has to be have 3 entries, and that's going to equal to my vector y. When I multiply this out, right, I multiply this row by this column, and I get a11 x1 plus a12 x2 plus a13 x3, and then I multiply this column, the second row, by the next entry. So I have a21 x1, a22 times x2, and a23 times x3 is equal to y2. And then I have my last row here. So what you notice is this here is just the first column vector of my matrix A. So I can rewrite this as column vector a1 times x1, my scalar x1, plus column vector a2 times my scalar x2, plus column a3 times my scalar x3, and that will equal to my vector y. And just to expand this out, just to make sure that this, just to totally drive home the point, this column vector a1 looks like a11, a12 times x1, my column vector a2 times x2, plus column vector a3 times x3, and you can expand this out and add it, and you will get exactly these set of equations, right? Anyway, I'll let you do that. But this transformation from matrix to this linear combination of the column vectors of A should come totally naturally to you. So make sure you learn this. Going back to this last statement that the range of A is equal to the span of the column vectors of A, we can look at this definition here, that the subspace W consisting of all linear combinations of a set of vectors, which is exactly what the range is. It's a span, or all the linear combinations of this, is called the subspace spanned by S. So this here, what we're going to see is that this is a subspace, which leads us to our next theorem. The theorem is the range is a subspace of Rn. So if A is an m by n matrix, then the range of A is a subspace of Rn. And I am going to leave this without proof, but I will do an example. So we want to describe the range of this matrix A, 1, 1, 3, 1, 2, 1, 5, 4, 1, 2, 4, negative 1. This is the same matrix we had found the null space for in a previous example. So to find the range, we are looking at y such that ax equals y, and we can do this looking at the augmented matrix of A with the column vector y. And this matrix is row equivalent to 1, 1, 3, 1, y1, 0, negative 1, negative 1, 2, y2 minus 2, y1, and 0, 0, 0, 0, minus 3, y1 plus y2 plus y3. So this gives us y1 and y2 are free, and then y3 is equal to 3y1 minus y2, and that will be the range of A. Now we've defined the null space and range. We do have two more things to define, which is the column space and row space. So if A is an m by n matrix with columns a1 through an, and rows little a1, little a2 through an. So now these are not just single entries, they're actually representing the rows. Then the column space is equal to the span of our column vectors, and the row space is now equal to the span of our row vectors. We're treating each row now as a vector. So for example, here, if I have my matrix A, then my row space is the span of treating the first row as a vector now, 1, 2, 3, and this row here, 1, 0, 1, as another vector. So the span of my row space is equal to my 1, 2, 3 times some scalar, x1, plus my 1, 0, 1 vector times some scalar, x2. This theorem here will be helpful in the next chapter. Actually, everything in this chapter is helpful in the next chapter, but I thought I'd just, for some reason, call out this theorem. So let A be an m by n matrix, and suppose A is row equivalent to the m by n matrix B. Then A and B have the same row space. So just kind of looking at that, maybe that's not so surprising because A is row equivalent to B, meaning the linear systems represented by matrix A and B have the same solution. And then this theorem tells us A and B have the same row space, which again is sort of like saying they have the same span. So for example, let S equal to the vectors v1, 1, 2, 1, v2 is 2, 3, 5, v3 is 1, 4, negative 5, and v4 is equal to 2, 5, negative 1. So there exists a set of vectors T, W1 and W2, in R3 such that the span of S is equal to the span of T. So here we have 4 vectors, but we're saying we can span the same space with only 2 vectors. And one way to approach this problem is by saying, well, if we know we can span with only 2 vectors, that means 2 of these vectors must be linearly dependent on the other 2. And so we could go and find which vectors are linearly dependent. But we're going to use this theorem as another way of approaching this problem. So we have our matrix A formed by the vectors. So here's vector v1, v2, v3, and v4. So we can look at A transpose. And remember, A transpose is when we take the rows and make them into columns. So this way we can look at now the row space, because now we're treating the rows as columns and we can see what they span. Well, this A transpose is row equivalent to this matrix. So I just did a bunch of elementary row operations and got this matrix here, which I'm going to call B transpose. And these two have the same row space. So looking at the row space of AT, that means I'm taking this row and this row, these 4 rows, and looking at the span of the 4 rows, or all the linear combinations. And I'm saying similarly, we have the span of B1, the first row, the second row, third and fourth row. And by our theorem, since these are row equivalent, they share the same row space. So this span here is equal to this span here. Now if A transpose and B transpose share the same row space, right, then the span of A, the original vector, is equal to the span of B, which I haven't written. Oh, here, I have written B. If this is B transpose, then this is B. And therefore, the span of B can be rewritten with just 2 vectors, 1, 2, 1, and 0, negative 1, 3. There was a small jump here, which is A transpose and B transpose share the same row space, implies the span of A, the columns of A, is equal to the span of column B. And that is true simply because A transpose row space is equal to the span of the column vectors of A. And that is because A transpose rows is equal to the column vectors of A. So the row space of A transpose, so that would be 1, 2, 1, all the linear combinations of these rows is equal to the linear combination of these columns. And you can see that is true because the linear combination of this row, it starts with 1, 2, 1, and that's the same as the span of A, which starts with 1, 2, 1. So this little fact here is important to remember because this theorem is useful specifically because you can do this little trick here. And again, what we did is we used this theorem to kind of whittle down these vectors into into a smaller set that spans the same space. You will see in other examples and in one of the review problems that if I had looked for the linearly independent vectors, and then I would have whittled it down to 2 vectors that were either v1, v2, v3, and v4. In other words, 2 of these vectors would have been in my final answer for 2 vectors that span the same space. However, using this method, you see you get 2 vectors that are not one of these original 4 vectors, but these 2 vectors span the same space. Okay, now we've covered all the material in this video. We had a review of linear combinations and dependence, and a linear combination is just scalar multiples times each vector, and then we add them together. We talked about the span of a set of vectors, which was just the set of all linear combinations of that vector. We talked about the null space, and those were the vectors that A times those vectors equals 0. So it's the vectors that get sent to 0 by A. We talked about the range, which is simply the vectors you can reach with AX equals Y. And then we talked about the column space, which is the span of the columns of a matrix, and the row space, which is the span of the rows of a matrix. And we had this last theorem that said if A is row equivalent to B, then A and B have the same row space. So now I have these 4 problems for you to try. So pause the video, give them a try, and on the next slide, I'll have solutions for you. Here is the solution for the first problem. A solution for the second problem. Here's the solution for the third problem. Here is the solution to the fourth problem, which I had done 2 different ways, and you'll notice when I used linearly independence, I eliminated 2 and I kept 2 of these 3 vectors. I kept the 2, 2, negative 1, and the negative 2, 1, 3 as my 2 vectors to span the space. When I use this other technique, you can see that one of the vectors I have is not even one of the original vectors. Nevertheless, these 2 vectors span the same space as these 2. And that's it for this video. Thank you for watching.